And welcome to Ladyada.
Hey everybody, and welcome to my desk. It's been a busy week. I'm a little under the weather this weekend, but we do a lot of stuff over the weekdays, and so we can see what's on my desk. Let's kick it off with reviewing the TLV 320 DAC 3100 that we did last week. So remember last week we talked about how I made a mistake with this breakout board design, which of course, yeah, here it is. Can you show the overhead real fast?
Yeah.
So this design, which had a few issues, it was noisy through the headphone when the speaker was on, and I think part of that might be because the speaker lines are brought out here underneath the headphones, so they're kind of close. I also wanted to bring up the bias and microphone detect pins because those could be used for like analog inputs. And also I totally screwed up this headphone jack configuration, which was causing it to be like really noisy because my headphones weren't grounded. So back to my computer, I fixed up this design. So this is the Rev B. I think this will be like the final one. And I don't think I talked about this last week. If I did, I don't know, and I get double dip. So the speaker lines are now right over here. So I just kind of like zooped them so they're like nicely separated with a big like ground. There's a ground plane underneath here, which is really nice. So there's no current. This high high amperage current isn't going to is no closer than is on the chip, basically, right? Because the pads are a couple millimeters away, anyways. Headphone is over here. I did scooch this out a little bit and I got rid of one of the mounting holes, but I think that's okay. I think like these two mounting holes are the most important, right? Because if you're going to mount this on something, you want to have the headphone or the speaker plug in easily. I fixed the mix up with the microphone and the ground, and then I brought out the mic pin, which connects to the third or fourth pin on the TRS, and I also brought out the bias pin. And this pin is used to provide a mic bias for if you have, a headset with a built-in mic. It's actually a little electret mic inside. It's like actually like dead simple inside. They're very inexpensive. There's a little electret mic in there, and then the driver has to provide the 2-volt bias that you feed into it through like a 2K resistor or something, and that will give you the JFET bias for the electret mic signal to come through. You can also use it to detect, when the buttons are pressed, or it's also used for the microphone detect. And it's also, if you're not using the microphone detect, like if you're not using like headphone detect, it can be an analog input that is used to change the audio level. So you can have like a potentiometer that is connected through the DAC itself to like change the audio, which I thought was kind of a cool thing. So, with the driver, like pretty much working. Like I have to finish testing all of the weird ass details. Like a tone tone generation wasn't quite working, but now I think it could have been this bad ground because it was like, I was like, why are the tones so quiet? But if I had no ground, then the difference between the two ears would be so small that like I wouldn't hear it. So I think it would work. And then headphone detect wasn't working, but I think that's because again, I got those two lines mixed. Rev B. I think I got it going. And, like I said, we're using this on the Fruit Jam board, which, of course I want to get out because it's a cool little design. But I also want to use it I want to use that amp in a bunch of things, including a revision of the audio effects boards, because the audio effects boards are great, but they use the VS1000 and I'm like so sick of this chip. It drives me crazy. And we can do something so much better with, RP2350 chip. So, but the nice thing about the VS1000 is it had a headphone / speaker driver built in. Like that was the cool thing. So I needed to find an all-in-one inexpensive DAC chip that had at least a line, speaker output in order to like make the balance of it work. Because nobody wanted the line out. That was actually quite rare. Most people wanted to drive speakers. Okay. Next up, a new design that I did is this triple bonnet. Okay. So what is this? So the RGB matrices that people love. I remember we were one of the first companies to drive them, and I remember Mr. Ladyada and I, we were walking to Chinatown, and I saw like these matrices on, like, I don't remember what it was, but it was on either a bus or like a storefront. And I looked at it and I saw the back and it said like HUB75. And I was like, I bet I could just get these and I could probably just drive them. Like they're not, I've seen large displays, but I never got to see the little panels up close. And then I contacted a factory that made gigantic displays and was like, can I just get some like, extras? They sent them to me and we figured out, got them working on an Arduino Uno. And now people love them. They're a great way to make large displays with lots of LEDs. But you do have to do this like very fast driving. They don't have built-in PWM. You like literally are just scanning every line one after the other. With the new Raspberry Pi 5 computer, they have gotten rid of the direct connection between the Broadcom chip itself and the GPIO. Like before, when you toggled pin 27, that was like the GPIO on the chip, which is like a little dangerous because it's like really easy to fry the chip. But moreover, you're limited because it's whatever GPIO the chip has, and also is the chip 3.3 volt safe? And like the latest chips are not going to have even their IO might not even be 3.3 volt safe. And so the new Raspberry Pi 5 has the RP1 chip, which is the predecessor of the RP 2040, 2350. And it's, I think, a PCIe bus to GPIO expander, basically, which means that it's really awesome for, having lots of extra GPIO. It's great because, you can do PCIe. It has like all the stuff built in. But what it doesn't do so great is fast pin toggles. Doesn't do that anymore. You could toggle the pins pretty fast with memory mapping on a Pi 4. You cannot do that anymore on the Pi 5. Instead, you have to go through the RP1 chip. And like I said, it's much slower, except if you use the PIO capability in the Raspberry Pi 5, which only got released like a month ago. So it's if you haven't heard of it, it's new. You can now program the RP1 chip to run PIO programs, and you can buffer data to it. And so if you want to drive NeoPixels, which we can do now, you tell it, hey, run the NeoPixel PIO program, and you just have to feed it like the bit stream, right, which is much less than the pin toggles. You just tell it, here's 16K of data I want you to write, or 8K of data, and it will just go off and do it and tell you when it's done. Upshot is you can now drive RGB matrices through this, and even though it's very, very fast, you do eventually reach the limit of the bandwidth between the Pi 5 and the RP1 chip. And so if you want to drive big displays, you want to have a triple bonnet. Why does this make sense? Because, oh wait, this is the old version. Hold on. I changed it, then I forgot to save it. Hold on, development. Plus my Dropbox didn't sync, which would be sad. Okay, no, now it's fine. So for the triple bonnet, what we do is we have 3 connectors, but the output enable, clock, latch, and the 4 address pins are all shared. And the adder E pin. The only thing that is different is the red, green, blue, the 6 pins for the 2 lines of RGB. And so as you add each new connector, you have a full new data path. Sorry, full new data path for RGB matrices, but you're not using significantly more bandwidth on the RP1 because you packetize all this data at once, and it's only 50% more, if that. I don't even think it's 50% more. I think that you probably can optimize the packing a little bit. So these basically you just have to use like every single GPIO available on that 2x20 connector, including the I2C pins and the UART pins. But chances are you're not using those anyways if you're driving a big display. But you can get up to 3 matrix panel outputs, and updating the PIO to do so I think is not too complicated. I'm going to let Jepler do it. Jepler's going on vacation and saying goodbye to his Adafruit adventures in about 4 weeks, but hopefully I'll get this PCB back in time and he can take a look and maybe get the updated encoding working so you can drive the 3 matrices. I use the default pinout I use here is the same as the like active 3 in the Raspberry, the original R Pi matrix driver for the Pi 3 and the Pi 4. But to be honest, I'm kind of like, you know what? I'm moving forward to the Pi 5. Like, I think people should just like, if you want to drive these matrices, you should just go to the Pi 5. I don't see there's any benefit to trying to get this. Yes, if you have the old hardware and you happen to get it working, but honestly, just the Pi 5 is the future, and there's going to be a lot of them, and they'll work well. So what I did with this design, there's no real-time clock because, to be honest, the Pi 5 has a real-time clock built in anyway, so there's no benefit to having an off-board real-time clock. This is a little switch that lets you change which pin is at or E. Either it's the 4th pin or the 8th pin. Those seem to be the 2 most popular ones. If you're not using port 3, you get I2C, so I put a little stemma QT port, in case you wanted to have a sensor or something added on. Although I was thinking, maybe there's a way to expose the EEPROM, like the hat I2C. It would be so cool if you could access that somehow. Maybe with the device tree overlay, you can hack it. And yeah, you get 3 outputs, no power supply management. Again, if you're dealing with 3 outputs, then the amount of current you're dealing with here is like 10, 20 amps. You're not going to put that through this PCB anyways. So I just left it off completely. There is no 5-volt connection in or out. Power is separate than data. You do the data separately. But the nice thing is, we have level shifters on everything to get you nice, clean 5-volt output. And this should work great for our large matrix displays. I would be very happy to be done with this. I feel bad for the developer of the R Pi matrix library. It's like thousands of people are using it, and it's like everyone's using it with a lot of like weird ass AliExpress knockoff hand wiring, and it's always a pain. Ever since we've had a Bonnet matrix, it's like we still have a lot of tech support questions, but at least the wiring, it's like you plug it in, like it usually just works. Okay, so that's the matrix. How are you doing on time?
You're at the 13-minute mark.
Okay, great. All right, and finally, with the weather getting a little nicer, I'm going to finish up. I designed this in September, and then it just got like unbelievably cold and rainy out, and I was like, I don't want to go outside and do GPS projects. This is a GPS module from u-blox. Let's go to the overhead real fast. I love this like little DigiKey hand thing.
Yes.
So this is
us being friends with
friends. Well, this is I'm about to talk about being friends with robots.
We're about to be friends with robots.
This is a little stemma QT breakout. Technically, it's smaller than the ground plane required for this module, but it seems to work just fine. This is the u-blox M8Q SAM. And u-blox is known as like they make the best GPS. When I say GPS, I mean GNSS, Global Navigation Systems. Is it GPS in America, American #1. But of course, there's Galileo, Beidou, and GLONASS for other, continents, countries, and stuff. And this can receive messages from those satellite systems. One thing people always ask me is, oh, like, is my GPS broken? There's like a nick in it. No, that's part of the tuning procedure. I want to bring that up every time because we've had so many customer support questions saying like my antenna is damaged. It's like, no, this is actually good. If you see these nicks, it means that they've tuned the antenna, and they do that by just taking a little bit of material out.
They might want to put a sticker.
I know.
If we're gonna have to keep dealing with this.
To be honest.
What was the thing that we used to have to deal with? Oh, there was plastic film on like one of the screens. No, sorry, there's plastic film on the acrylic, and people would be like, "You guys did a terrible job. There's this like paper on top of the acrylic."
Remember the guy who like had a total meltdown about the EL, is the EL plate, and he no, he thought there was protective film, and he tore it in half, and I'm like, what were you doing?
Yeah,
like totally Godzilla did. Okay, anyways, so this u-blox module, it's a GNSS. Uh, we don't carry u-blox stuff as much, and I feel really bad because Michael comes by like every year, and like it's been like 8 years, and he's like, "We need to do u-blox stuff," and I'm like, "Oh, I'll get to it." But the weather's really good, so I thought I'd get back to doing some more GPS stuff. We carry these modules, and they're fine. The ones that we stock now, the Ultimate GPS, but some people do really want slightly higher quality, and they're willing to pay for it. These are more expensive than the low cost ones. What's nice about these is that first off, the antenna is a fairly good size, and they have both I2C and UART output. So if you go to the scope,
Scope time.
That'll be fun. So this is the output from the TX pin. And what's great is, it comes up and it immediately starts piping out data in the standard NMEA format. If you are a robot, maybe you can look at this image and just like automatically recognize it. You can also read data from this in I2C. So let's go back to the overhead. So there's I2C. There's some also that have SPI, by the way, but this one has I2C. Now, it's a little confusing, but I read about this and I understand it now. The UART and I2C. So there's a way to just read like raw data from the I2C by like you read from address like EF or something. I don't remember. Maybe I'll show the code. And when you do that, you'll get basically the NMEA data. It's like the text data, but you're getting it over I2C. And that's fine because, maybe you don't have a UART. Like that is kind of nice if you don't have a UART. And especially on Arduino Uno, you only have like one hardware UART used for uploading, or ESP8266 where you don't have one, whatever. You don't use software serial because it sucks. Or maybe you're using your UART for something else. Like maybe you're on a Raspberry Pi and you're like, I don't have the hard, I don't want to use the hardware UART. You can use I2C and you can get that same data very quickly. And then, you still have the pulse per second output as a GPIO. You have IRQ as well, and a reset pin. But then there's this other thing called UBX. So let's go here. So on the computer.
Yeah, I'm getting there.
Yeah.
Sorry.
That's okay. Okay. So you can get NMEA data like that, like, $GPRMC with, the star and the 2 hex digits at the end, CRC. That works great. But if you want to get fast data, or you want like more, there's like maybe there's not a sentence for what you want, or you want to like send and receive data much faster, there's the UBX protocol. And the UBX protocol is 475 pages long. And basically there are like all these things. For example, jamming interference monitor. So, you want to know if somebody's like messing with your GPS. It can do some automatic detection of like, hey, their signal is my analog front end is getting overwhelmed or something. And to do that, you send these messages with checksum, with a header, with a class, an ID, and the config, and then it sends back the bits. And this is an image, which I really wish it wasn't. That's okay. And there's another bit field, and it tells you all of the different bit field configurations. And it goes on and on and on and on. You have to put it into this mode to start, and you can get all the normal, like you can actually get NMEA through it as well, but you can also get like this more compressed format, so you don't have to parse all these. To be honest, it's a little easier on parsing, right? Because there's no like these looking for commas, looking for is it like, dotted decimal type stuff. They did design a C-based protocol parser, but then they discontinued it last year. And so I'm looking around. There's actually a couple of people who've done like parsers. There's a lot of actually C parsers, and there's a couple of Python parsers for the UBX format. It's totally a beast. It's huge. And so I wanted just to test, like, before I make this hardware. And again, I think 98% of people are just going to use the NMEA format anyways. But I wanted to just like, can I get this into UBX format and verify it? And I was like kind of dreading writing this code because it's really, it's not gnarly, but it's like there's an acknowledgement, and like the acknowledgement might be interleaved with other messages, and it's like there's just like a lot going on. It's a very complicated protocol. And so this is where I went to Claude 3.7. So I haven't used Claude 3.7 yet. I look at like the AI minute at the end. And I was able to get it like 3.7. I will say it does kind of go a little nuts. And I had to kind of tell it like, yo, like cut it out. But I did get it to both make the basic I2C interface and also a pretty nice job of doing the UBX protocol parsing. And there was like, it wasn't perfect. There were a couple situations where it didn't understand. I'm trying to remember. It accidentally set the I2C address to 0. It didn't understand like what the mask meant. And there was a couple things where I don't even remember. The checksum I got right, but it wasn't perfect. It didn't completely understand everything about the protocol. So I did have to kind of help it along, but we did eventually, without too much effort. Oh, here was the thing. We had like Claude did this thing where he didn't understand like the stream interface for Arduino. There's write 1 byte and there's write multiple bytes. So, I don't know. We got that working. We figured, oh, right. And I remember what it was. For the u-blox interface, this was somebody in this stream is going to be like, wow, I'm going to save myself days of time. For the u-blox I2C interface, you cannot write less than 2 bytes because it thinks that when you're in UBX mode, because it thinks you're setting the register. So if you do have to send data to the UBX interface, it has to be more than 2 bytes. And so you can't use the single byte write for I2C. You have to write like the full buffer at once, or it gets like very upset. So that was what I got confused at. But we did eventually get it working, and it wrote this code for me. And hold on. This is okay. So she said it. So it does the UBX. It starts with like the current data. The only thing is, once you have it in UBX mode, you have to do a hard reset if you want to get out of UBX. I don't have the command for getting it out of UBX mode, but it's able to transmit. And what I really like is about Claude 3.7, like one of the things, again, it's not perfect. One of the things I really liked about it is all the little details like, oh, could you handle every single type of like error return that could happen? Also, when you like print it out, could you like do this pretty printer for me and tell me like, the UBX class, what you received and the response and what the type is. I mean, it's very like wordy, but it's really good for debugging. I don't know if I'm going to continue working on the UBX interface, but I did think it was a good experiment with using Claude 7 to write complicated code. Only thing is the context window, again, not that big. So if I was going to implement all like 5 trillion UBX messages, I'd probably start a new context chat for each one and give it the code as a project and just say, hey, I'm going to add this new UBX message. Then please do the code for that one. I'm also, again, I'm going to see like if I can use the u-blox UBX library. UBX lib is again abandoned, but maybe I can maybe Claude can digest some of that and rewrite it into an Arduino friendly format. We'll see. Okay, what were we at time?
You're up to 24 minutes.
Wow, that was 10 minutes of u-blox. But let's go to the great search.
Where in the world is that part I need? The great search with DigiKey.
The Great Search brought to you by DigiKey and Adafruit. Thanks so much, DigiKey. Every week, Ladyada uses our power of engineering to help you, yes, you find the things you're looking for on digikey.com. Ladyada, what are you looking for this week?
Okay, so this week I've been working on implementing and using the SAM M8Q GNSS GPS module. And I wanted to see, first off, like what other GPS modules were available at DigiKey from u-blox. And second, are there any other ones that have a built-in antenna? Now, I've designed GPS stuff that doesn't have a built-in antenna, but boy, it like makes things a lot easier for people if it's like you don't have to plug something in, the antenna can't come loose, whatever. So let's look at DigiKey. And let's look at u-blox. Normally, I don't look at a particular vendor, but in this case, I'm looking just at one vendor. So receivers. Okay, so this is lots, and they have a lot of different stuff. And they've got, they've been around for a really long time, at least 20 years, because I remember when I was interning right out of college that u-blox, the Neo series was like the hot new thing. And they were pretty sweet. Okay, so let's look at only u-blox. Let's look at active. And I just want stuff that's normally stocking. Okay, let's just see what we've got. So there's like about 45 like standard stocking modules. And let's start with, like some of these have like built-in antennas. So let's look at ones that have built-in antennas to start, because I do want to, let me see, antenna on board chip, on board patch. I'll do PCB trace too. I don't know how you can do a PCB trace antenna for GPS. Okay, so these are the modules. So this one actually is cute, but wow, this is a really tiny little antenna, but maybe it's like for very small wearables. This one, I think there's some confusion because it does not seem to have an antenna built in, unless it happens to be, maybe they are saying you expect to use a trace antenna. This is the M10Q. This is one of those limited ones. And this is the one I'm using now, the M8Q. And I'll be honest, I was a little bit like, well, what's the difference? Because the pricing, it's a little less expensive for the M10Q. What's the difference between that and the M8Q? And so I did a little bit of a deep dive between the two. And the M10 series is newer. That 10 actually means it's the 10th generation versus the M8 is the 8th generation, which I actually really like. I actually wanted to have an aside here. Whatever you do, if you're making multiple versions of a chip, don't make smaller numbers be newer. This happened with like these Zigbee modules that I used once, where like series 1 was better and newer than series 2 or something, and it was like incredibly confusing. Thankfully, the numbers only go up. Thank you. Only increment, please. So M10 is newer. And the amount of current used by the M10 is like significantly less, which makes me also wonder if I'm maybe reading this data sheet wrong. Because it says here for like acquisition and tracking that the current is about 25, 30 milliamps, which is standard, right? That's what I've seen for most GPSs. But here, it says that the indicative power requirements are like half or 1/3. Like if you're using just GPS, it's only 5 milliamps, which is pretty amazing. Well, this is in power save mode, but even continuous mode, 8 milliamps. If you happen to have all of the Galileo and GLONASS and Beidou, like a whole 10 milliamps tracking, 13 milliamps, so like 1/3 as much current, which is amazing. So I didn't realize what a significant difference, because I'm so used to like, oh, they're all about the same, 25, 30 milliamps. The M10 is also a tiny bit more sensitive, but the big change here is the incredible current savings. Okay. They're also pin compatible. So in general, I think if you were to pick which module you wanted to go with the M10. However, before I keep going, I did want to just show off the other. Let me get rid of the antenna connector. I'll tell you. So the vast majority of u-blox modules, this is the M10, but without the built-in antenna, so it's much smaller, much more compact. The vast majority of u-blox GNSS modules will require an external antenna, and u-blox does have external antennas, like big ones. Traditionally, if you're doing something with GNSS, if you're doing location tracking, either you want something really, really tiny, or the antenna can be as big as you want, right? If it's automotive or something, or like tracking like a boat, car, goods, the antenna can be quite large. But usually the GPS receiver is like inside of a little metal box somewhere at like the bottom of, and protected from the weather. And then the antenna is brought out and is like attached to the top. So while I personally think that these patch exposed antennas are quite handy because they're easy to use, they're not typical of use cases. So like the Neo series, and then you also might wonder, so most of these, you know, $15 and $20 or so, that's not unusual. And then once in a while, you're going to see one and you're like, whoa, what's up with this module? Let me find one where it's like crazy expensive. Yeah, like these Leah M8s, $100. Suddenly it's like $90, $100, the MAP. 128. So these are the RTK capable modules. So these use either cloud-based service or they have a two devices that can synchronize with each other, and they can give you centimeter level precision. GNSS will never give you better than like 2.5 meter. That's kind of the capability of it. If you need higher precision, you'd go to RTK. We'll cover it maybe in another great search. For this one, let's only talk about, unfortunately, you can't filter by price, but you'll see like either of these modules are like 15 to 30 bucks, or they're like 100 and $250. There's nothing in between. So if you're going to use this for a product, I think prototype with the ones that have the patch antenna, just for like ease of use. Like you just pop it on your design and you can at least get started immediately. But it does have to have access to the sky, so hopefully your office is near a window. If you don't, you'll need to put on an antenna connector, and then u-blox actually sells antennas, and they're a reasonable price and they're great. You know they're going to work. So check out, if you search for u-blox antenna, you can see these are all, you know, just a couple hundred in stock. On the other end, they have like little mounting. Sometimes they're magnetic, and they have an SMA connector on the other end. You can get them with different ones. 99% of the time, it's SMA. If you care about size, you can get MMCX or SMB. You plug it in, you put this outside, and of course, if they're fully weatherized and they're, you know, can be exposed to rain, wind, cold, heat, and whatever. But to get started, I would go with, where were we? And the one I think I'm going to pick up next, because now that I'm done with this M8, you know, I want to do another one. Let's do the built-in antenna patch. Although those little chip antennas were kind of cute too. I'm using the M8, but actually, ironically, even though it's cheaper, which usually means it's less good, it's actually, this one is going to get you much, much better power results. So this is the M10Q series from u-blox. So this is my pick for the great search. If you want a ready to go GNSS module, ultra low power, easy to use, and you can use NMEA, I2C, or UBX interface to read data from it.
And that's a great search.
Where in the world is that part I need? The great search with DigiKey.
Okay, that's it. We're out. Let's keep doing more stuff.
Bye.
Let's do a bunch of engineering.
Gonna go vibe.
Let's go do some stuff. Okay, bye everybody.
Later.